we like solving very complex problems, right? And we often talk about, a lot of the work we do in financial services, but we thought, which is another very complex environment that we like to solve problems in. And that's for our customers in the telco space. So we thought we'd show a very interesting demo that we've got. This one's for network operation centers, specifically positioned for mobile network operators or any kind of network operator. What this demo shows in particular is a dark NOC, which is a dark network operation center, dark nodding sort of towards a dark factory where there's no human beings. So it's basically just robots and it's fully automated. So there's no lights on the factory floor. But what we are showcasing here is an environment which is super complex because of the amount of data that's being generated. You can imagine that most MNOs have got hundreds, if not thousands, of physical infrastructure points generating a lot of log and telemetry data that's coming into a central place. And you've got humans literally monitoring a lot of these logs on the screen. So typically you find, network operations center dashboard, you've got, all of your different nodes, the neighbors, all of the health checks, the scores, if there are any alerts that are coming in, what the current status is, and what the network currently looks like, right? But what happens if something goes down, right? It can happen at any time of the day. It's typically a very complex triage process. You need to swivel across 6 or 7 different systems. So what we wanted to showcase was an end-to-end solution which uses very simple data processing all the way through to analytic solutions, to statistical modeling, to machine learning, all the way through to agentic AI, which is what we've got today. So let me switch over to the Anomaly Detection Hub. Right, so what we've got on the left here, we've got a network topology, which is a live graph of 14 nodes mapped to their approximate geographic locations. What we've got here is a model of the United Arab Emirates, and it's a dummy example, but it's a demo of 40 nodes. Each node is color-coded by its current anomaly score, so green means healthy, red means something's wrong. The timeline along the bottom represents specific 5-minute intervals, and each 5-minute interval is an aggregate of all of the network behavior that happened within that period, sort of brought together and scored. Right, so let's play this, and I've got it in presentation mode. So you can see from the graphic that there's all of this network packets. You can think of this like any normal kind of network. If we scroll down here, if we look at the line on the chart, that line is the line of our VAE residual score, which is a particular kind of machine learning model. Really what VAE does, it stands for variational autoencoder. It's a machine learning model which learns normal behavior, and it learns sort of what anomalous behavior looks like. And what it's able to do is discern between time periods where activity is okay, and then time periods where activity is not okay. And basically what it does is it's sort of just measuring how far the expectation is from what's actually being. So it's predicting at each time period what the activity should be, and if the activity is pretty different, then the score goes up. So what we've done is we've set this threshold score at 75%, right, which is a number you can see from the graph that these 3 nodes have really sort of lit up. The anomaly log is also populating, right? So if I scroll down here, you can see that there have been 3 elevated scores at each of these nodes, so Ajman, Sharjah, and UAQ, right? And it'll tell you which all of the connected nodes are. So the ones next to them, that's important for, and I'll explain that in a second why that's quite important. So if I scroll back up, and I play this step by step, right? So if I go next, so this is when things get interesting, right? So we've just breached that 75% anomaly threshold. What happens is that this, once that score is triggered, a 7-step autonomous agent pipeline is triggered. And I'll walk through each step, right? So the first step is event correlation, right? The agent starts by scanning the topology graph for related nodes. So it identifies that these 3 nodes in the center are all showing correlated signals. it establishes a temporal sequence. So there's something called cascading. So it'll basically line them up, and it'll say, okay, this event happened first, this, then this one, then this one. And effectively what that's doing is it's trying to correlate exactly where it's coming from, so which ones are downstream and which ones are upstream, which alerts are upstream or downstream. And what it's trying to really do is build a causal chain of what happens. So it's trying to stitch together and figure out where this thing's happening in real time, right? So if we continue and we're stepping through this step by step, and I'll play the demo end to end, what it then does is it goes into a root cause analysis agent. So that agent will then go and dig into the metrics. So which specific signals spiked on that particular node. So if we've said, okay, well, we believe that it's Ajman, and we've picked up that there's a specific kind of equipment failure, what were the causes for it, right? And can we tell? So you can see that there was a hardware fault causing interface flapping, and that resulted in call drop rate increasing by 340%, right? So we're trying to diagnose exactly where that's coming from, and what we can even do is look under the hood of the machine learning model and say, okay, well, from our feature attribution, which is basically just saying, explain to me the ML predictions of which features or which inputs within the network sort of data set are causing these anomaly scores to go up. You can see that the packet rate has gone up, or rather it's contributing most to that prediction. And then likewise the rest of these metrics like bandwidth utilization, CPU usage. So there's a whole lot of activity across the input data set that doesn't look 100% right. Then what the agent will then go and do is look up that particular device's manual. So it queries a knowledge base, and it'll go and look at specific sections. So it'll look at traffic storm control, CPU utilization analysis, and then what it'll do is it'll try and classify the fault according to a specific fault matrix, right? So then it'll say, okay, well, we've correlated and matched these symptoms against a particular fault taxonomy, and then that will then give us a classification of what the severity of the fault is. And then we can break down exactly where it's coming from, what the occurrences are, and explain not only what's happening, but why it's happening. Sort of walking through the last two steps. What it then does is it puts together a plan of how to remediate this. Now, you can imagine this is happening in real time. So imagine you're a network engineer, this happens at 2 a.m. You need to look across 6-7 different systems. AI is basically doing this, and it's scanning across all of these different systems, and now what it's done is it's correlated, it's pinpointed, it's told you exactly which node is down, why it's down, what the symptoms are, what the fault is, it's classified the fault, and now it's going to put a plan together for you, and it's going to say, okay, we need to do 3 things immediately. We need a failover to a backup device, so switch the traffic from these 2 edges to another 2 edges, reroute traffic, which is obviously part of the first point, and then notify your NOC team, right? So then actually raise a ticket. What we've done in this demo, and one point to note, is this was built in collaboration with Quintica, which are our partners in ServiceNow. So on the left, you've got the data lake, which is doing a lot of the data processing, the machine learning modeling. And then on the right, you've got the system, the data lake, which is the brains of the solution, talking to ServiceNow, which is the system of action, right? And that's generating all of the incident problem tickets, all of your alerts, and then finally being able to actually execute action within the graph. So you'll see it will now actually go and trigger specific API calls. So it's failing over to this particular device, rerouting traffic, and then it's sending an alert. You can see we've gotten all of our API responses as successful, rerouting traffic successful, and then the alert is pending because they're still waiting for that to come through on the system. Now that's success, right? And if we play this all the way through, you'll see that that's been triggered, and because the traffic was diverted, now your VAE score has gone down, and the rest of the nodes in the graph are sort of green again, which means that activities remain back to normal. So why is that so important? I think it's important to always ask ourselves the so what question. So obviously mean time to detect and mean time to resolve are metrics that keep network operations leaders up at night. So every minute of degraded service costs revenue and erodes customer trust and burns engineering hours. And obviously, we've made the point a couple of times that traditional monitoring tools generate alerts, and that's really just not enough anymore because there's so many alerts that are being generated. There's a ton of fatigue. So what you really want is not only a system that tells you that something's wrong, but it's telling you what is wrong and it's telling you how to fix it, and then it'll even take a step further and actually fix it for you, right? So that is the agentic layer, which is the real unlock.